those of you who have been to Saturn before probably already know Jeremy, and for many of you, he needs no introduction because he's been to most of the Saturns since they've begun, but he's wearing a new hat this time, so... Every time. No, I wasn't going to say that. So Jeremy's engineering director with Google, leading a number of teams that develop core components for Google's production cluster management infrastructure. And prior to Google, Jeremy was chief architect for xCommerce, which was a business unit of eBay, where he was technical lead on an open commerce platform. And prior to that, he was senior architect, co-founder, CTO, and various other titles at Yahoo, Vistaprint, Fidelity Investments, Microsoft, AOL, Quack.com, and I've probably missed one or two, but I got most of them.
Did you mention the SCI?
And that's right, and he worked for the SCI back in prehistoric times. So please welcome Jeremy Carrier.
Wow, that sounds ridiculous. But all true. I was actually just trying to get Rick to like mutter as many like buzzwords in one intro as I could. So I'm going to talk about some big data kind of concerns, and I like kind of did this kind of clever scratch out thing up there because this really isn't anything to do with big data. Not that I have anything against the terminology, but these are really just general kind of systems things. And I'm going to, where I can, talk about some internal Google technology that we use to address some of these challenges that I'm going to talk about. After I give you a little bit of sort of Google sort of intro stuff, which I generally think is fun for people to hear. But I'm also going to talk about my experiences using various open source technologies to address, again, some of these same challenges. My time at Yahoo and eBay, working with Hadoop and HBase, and some hybrid architectures. Actually, I didn't know the term Lambda architecture, but stuff very aligned to that. We'll have to talk about HBase hotspotting sometime. So I do this clever kind of controversial title to try to get people to come to the talk. Is it easy, really? Well, it's not actually all that easy. Google's been working out on MapReduce and on the MapReduce infrastructure for a really long time, and its successors and their successors. But in 2008, Google sorted a petabyte in around 6 hours on 4,000 machines. Stats like 48,000 hard disks. Turns out that 48,000 hard disks spinning for 6 hours, some of them are going to fail. It's actually pretty hard to get them to be reliable. And then in 2011, the benchmark was done again in 33 minutes on 8,000 machines, so 6 times better. So there's a lot of hard technology, right, that goes into making this work. But the actual writing the MapReduce to do a sort, or even to compute PageRank, is really simple. Like, that's not a complicated algorithm. You go and you can, once you understand the fundamentals of MapReduce, writing the actual algorithm for these kinds of problems is actually not the tricky bit. You can do it once fairly easily, but it's not about doing it once. It's about doing it over and over again so that you can actually extract business value from it. So as Rick said, I'm an engineering director at Google based in New York. New York is Google's second biggest site. If that was known to the Googlers in the room. After California, we have, 4,000 people-ish, something like that in New York now. So it's a big site. I work on, as again Rick said, cluster management, which is a kind of buzzwordy term for an even more buzzwordy marketing lingo. Basically, the operating system that runs that Google computer, right? If you imagine Google as one big global computer, this thing that we call cluster management is kind of the operating system that makes that work. And Ivan's, I'm sure, like cringing. All the Googlers in the room are like, oh. But it's the easiest way to kind of explain it. There's lots of pieces to that. Stuff from doing scheduling to doing monitoring and logging and debugging. So there's lots of pieces. And down to the Linux kernel, and then down to the hardware, and down to the networking. Not that I work on all of those things. But a little bit of background, I think, just to kind of contextualize. So that's a Google data center. It's in the Dalles, Oregon. Turns out it's only about... Dalles, sorry. Damn it. I should be careful when I'm actually in Oregon. I've never... Dalles, sorry. The Dalles, which is only, I realize, about 90 minutes from here by car, it seems. I've never actually done this talk that close to the data center before, which is kind of cool. What's actually really neat, so here's the Google Earth or map view of it. And it's not particularly interesting, just like 3 white boxes, but you'll notice that it's got a really tiny parking lot, right? There aren't that many people that actually work here. And those buildings are full of computers, right? Lots and lots and lots of computers. But there aren't many parking spots. And that's actually a really important part of what makes Google Google. So again, some more context. So those data centers contain one or more clusters. That's a physical group of machines that live in racks. Racks are grouped into clusters. There's some networking infrastructure that is well beyond my ability to explain, even if I could. And then those clusters have a logical management overlay concept called a cell. So a group of machines is managed as, say, a compute cluster in one cell and a storage cluster in another cell, or a storage cell. So 2 separate sort of management overlays on one physical infrastructure. And then how do users actually interact with this compute platform? So the fundamental concept in this world is a so-called job. So a user submits a job. A job contains, some number of tasks. It could be 1. It can be thousands. Those tasks actually then run on physical hardware, physical machines. One interesting peculiarity about the way Google thinks about these problems is that these things have so-called configuration. And that configuration is everything from which specific software am I going to run, some reference to a bag of bits someplace that's a binary that I'm going to execute, but also things like what are the resource requirements of this thing? How much RAM does it need? How much CPU does it need? And then all of the runtime parameters that control the behavior of the application. All of those things we call configuration. All this is going to hopefully come into relevance in a second. And then we have 2 kinds of jobs. We have the so-called services, which are user-facing, latency-sensitive. So this is you opening your Gmail, doing a search, getting an ad served to you. So there's a user waiting. Everything else we call batch, the stuff that is not latency-sensitive, by most sort of ways of reasoning about it, not any less important to the business, but can generally be preempted, can be repeated because it's throughput sensitive, not latency sensitive. And then there are a bunch of other things to consider, like priority and periodicity and dependencies between jobs. So this is a pretty complicated problem. The unfortunate truth is that there are lots of different kinds of failures that we have to deal with in this global compute infrastructure. You can see some sort of statistics there. But what it boils down to is if you have a service running on, say, 2,000 machines, it's going to see something like 10 crashes a day. That's, you have to engineer for that, right? It's a normal part of doing business. And then there are a number of ways, there are a number of things that kind of cause these things. Typically, networking failures, power problems. Getting hit by lightning is often small, slightly troublesome. Various kinds of human errors of sorts that we generally don't talk about. And then there are a bunch of rare things. Occasionally, wild dogs discover that they really like the taste of the lubricant that was used to run the cable through the conduit in the the back of the, and they chew through it, and problem. The dead horse one, I think it was a farmer who was burying a horse and cut through a cable. The copper thieves are funny because they're really stupid because it wasn't copper that they were actually trying to dig up, it was fiber. They thought it was copper, but it wasn't copper, it was fiber, but they still cut through the cable. And then, drunken hunters and sharks, and I'm not actually kidding, that's a shark chewing on an undersea cable, so I am serious about these things. I also heard one yesterday about a snake that got into a transformer somewhere. Problems. So what we want to do, right? My purpose, with this infrastructure is to run all the things, right? To make all this stuff work and make it work predictably in the context that I just described, right? So how do we sort of face the challenges to make this a predictable enterprise? So really, yes, we want to run everything, but then there are a bunch of other kind of constraints. We want the system to be predictable, right? We want our users to be able to understand what's going on. Google engineers are really picky, right? My customer is primarily the Google engineer. Some other Google engineer that works in ads or search or shopping or someplace, and they have opinions, right? And they want their stuff to work generally the same way every time, and not break. which is the next one. And then there's an interesting trade-off that we have, as many large enterprises do, between the resource efficiency that really large applications need and the so-called innovation efficiency or velocity that the small guys need. And we somehow have to serve both of those constituencies. And there have been many efforts at Google to try to optimize across that trade-off boundary. We want stuff to run with high utilization. I'm going to come back and talk about that later. Scale is probably self-evident. And of course, we want to do this as efficiently with respect to human resources as possible. So then I'm going to talk about a subset of these issues. If I say, hey, the MapReduce part's the easy part, what's the hard part? So it's these specific topics. And I'm going to skip over the two most boring ones, data movement and quotas and accounting. If you really want to talk about that, you can buy me drinks. So first step, build versioning deployment. This sounds probably like a fairly straightforward problem, right? But the idea is, how do I get the right version of software, whether it's a piece of infrastructure or a piece of application, an application, in the right place, at the right time, continuously. And when you have lots and lots of computers, as we do, this is not a trivial problem. And in fact, Ivan in the room works in systems in this area, so you can pounce on him after. So we need to figure out how to, first of all, build. That's Ivan's domain. How do we take the source code that we've got and jam it all together into something that a computer can run with the right pieces of dependencies and all that stuff. So yeah, package it all up, get one kind of unified bundle, and my team does some of that stuff. How do you then get it out into the global computer that we've got? And then how do you actually sort of get it ready to run? And this is all before we even think about scheduling an actual task to run someplace, right? All of this is prerequisite to that. And it's got to work every time, right? Like this is one of those things that if you subscribe to the basic philosophy that velocity is the most important thing in software, we can't afford to kind of have this break. And this is another thing that Ivan is very concerned about. So this is written up quite nicely, a lot of this at Google. So our engineering tools blog. A key thing that we recognize internally is that automatability of systems is key, because all of our automation, all of our sort of tooling that we have across the company has to build on top of these underlying building blocks, so that we don't have to have a human that copies the bits to the right place. All that stuff has to happen automatically, because we can't afford to do it at scale and be efficient. Then there are lots and lots of open source pieces that partially cover this space. So Jenkins is an open source continuous integration framework. In the Hadoop ecosystem, Apache Ambari. I'd be interested if you folks have had any experience with Ambari. I don't know if it's actually catching on, but Hadoop is notoriously difficult to deploy and keep up to date. Ambari is intended to do that, because Hadoop itself Hadoop as a thing has got lots of pieces that have very finicky version dependencies between them, and you need to get the right set. So Ambari is intended to help with that problem. At the platform as a service layer, there's a offering called Cloud Foundry, and they have an automation system for doing build, deploy, and management. Then there's a group of tools that have seen a fair amount of popularity: Chef, Puppet, SaltStack. SaltStack kind of being, again, the most modern one. And then Docker. Someone mentioned Docker at a talk this morning. It's the new hotness, right? Everybody loves Docker right now. If you do a Google Trends graph on, put Chef in and put Docker in, and you see Chef go like this and Docker go like that. Everybody's hot on Docker right now. All Docker does is, it's actually really, really simple. It is a straightforward mechanism that lets you say, here are all the packages I want sort of deployed. It builds a file system image, and then you can tell Docker to run it in a Linux container. That's it. And if you want to do more complex things, bind these containers together or move them around, that's all your problem. But it gives you that foundation, and it's become very, very popular. Someone asked Scott the question this morning, actually. So then this configuration problem, I kind of alluded to this being a complicated thing. So the problem here is the so-called application control plane. So how do you actually control the behavior of one of these large distributed applications? So you have to think about things like dependencies, how you prescribe scheduling parameters, what its resource constraints are, and so forth. And you want to do that in a way that lets you avoid these detailed, brittle specifications of exactly how to do something. So if you say, I want 40 tasks on this rack and 20 on this one because you're anticipating, rack failures, that's going to be very brittle, right? Then you don't get much flexibility at all because you've taken control away from the infrastructure. What we want to do instead is use SLOs to tell the infrastructure what the constraints are, and then let the infrastructure figure out where to run it, how to scale it, by giving it things like number of tasks down. That's pretty good. Request latency is even better, right? I want to never serve at the 99th percentile greater than 25 millisecond latency. But better yet, what is the user really trying to say? They're trying to say, give me the best you absolutely can, but here's how much I'm willing to spend. Right? And that's still kind of an unobtained holy grail around the field in general. Thanks, Rick. And then there's open questions. How much expressiveness do we need? Can we do this? Can we separate the idea of infrastructure configuration from application configuration? And then doing all this without falling into the trap of, oh, hey, what do you know? I tripped into a Turing-complete programming language for configuration, which happens over and over again. Yeah. Service level objective. So SLI, service level indicator, that's the thing you measure. Service level objective, what you're trying to achieve. Service level agreement, what you do when you break it. So this one is, I'm going to skip over this one. Uzi showed up on a chart a little while ago. This is I just need to run this thing predictably over and over again. Sounds like a simple problem. It's actually conceptually simple, but you have to be reliable. You have to get it right every time. Hadoop has got Uzi, which I worked on at Yahoo, and I won't say any more about that. Usability. This is my favorite topic here. And unfortunately, Patrick, who saw Patrick Riley's talk this morning when he talked about Sawzall? Just a couple people, so I shouldn't even have mentioned it. I would have gotten away with it. So the basic problem here is that the community of folks that want to do big data extends beyond the equivalence class, the awesomeness equivalence class of Jeff Dean. Right? Jeff Dean is the guy that built like most of the first version of most of everything at Google, MapReduce and search and like Brain, all Jeff. So how do you make this technology accessible to more than this sort of superhuman person? Sawzall was an answer to that, and Sawzall was a now deprecated but long, which is why I should have just not said anything about Patrick's talk, but long popular domain-specific language for specifying at a higher level these large distributed MapReduce-like computations. And there were some, when Rob Pike and others wrote the paper and built Sawzall, they did some analysis and found that it was dramatically easier to use. And this is still something that we're trying to get back to. There are many offerings in the Hadoop community, Pig and Hive that was mentioned before, and Cascading and Cascalog, all frameworks and languages to try to make this kind of computing model more accessible to more people. And very related is this demand for interactivity. Google, we've got Dremel, which is our internal system exposed to our cloud platform users as BigQuery. Apache's got Drill, there's Spark and Shark that are also popular open source technologies. So increasing the accessibility, the usability of this technology so that more people can do more sort of discovery, innovation is still a challenge. This area is obviously so popular and exciting that I ran off the bottom of the slide. This is actually one of the places that I have responsibility for at Google, all of our monitoring and logging systems. So when we've got this global computer running mail and search and whatever, it turns out that it's emitting a fair amount of data, right? It's emitting logs, events, telemetry, right? Rates of things and consumption of things. We have to be able to work with that data and act on it, raise alerts, right? Inform humans. So this is a lot of data, right? We have a lot of those computers, and they produce a lot of this telemetry. But worse, the systems that do all this have to be at least as reliable as the systems that are monitoring, because the worst thing is having something go wrong and you not knowing it, right? And then I get a nasty gram from our head of SRE. This has been done horribly in the open source community, Like people try, but it's always an afterthought, right? Who wants to work on this stuff? So there's a very fragmented community or ecosystem of tools. Some, some better than others. Logstash, Elasticsearch, FluentD in the logging space, Flume that folks before mentioned, which is fairly popular. A bunch of sort of piecemeal solutions to the monitoring problem, awful-looking graphs, and so forth. There are many commercial solutions that are out there. So Splunk is very popular in the logging space. It works very well. There are a number of cloud monitoring solutions, one of which, called Stackdriver, Google acquired. We just announced that today, so that we could specifically accelerate our ability to offer our cloud customers, our external cloud platform customers, a better experience for monitoring their services. Okay, utilization. I mentioned this before. This is actually an opportunity. I mentioned that we have two kinds of workload at Google, the serving, production, latency-sensitive workload, and everything else. My team actually works on the so-called batch scheduler. That's the thing that exists to take this batch demand, right, demand for these non-latency sensitive jobs, and pour them in to fill the troughs in the serving workload demand. And we actually released some carefully sanitized data some time ago that was analyzed by the folks that wrote this paper, which is a good read. And they did this analysis that actually showed our cluster utilization. So the data that we released was the actual usage of a cluster of machines over some period of time. And it was sanitized in some way that didn't obscure the actual statistical important properties. So you'll note right here that this peak, which is the actual use of resources in this cluster, peaks at around 60%. That's really high. That's higher than most infrastructures run in the maybe if they're lucky the high sort of teens, right? So not that we do that well all the time, and there's certainly more room to improve because we're actually allocating, in some cases overcommitting resources and still not using it all. So we can still do better. And of course, there's different kinds of resources to optimize: CPU, network, disk, RAM. But this is actually a pretty significant achievement. This paper in Communications of the ACM is also a great read because the trade-off that comes with driving utilization this high is that you lose predictability, right? If I've got one computer and it's running a batch job, right? That's processing some piece of a map. It's a MapReduce worker or whatever, and it's churning along. But then demand for serving workload goes up. So there's a task on that machine that needs more resources to serve a search query. You have to evict that lower priority batch job. Well, doing that takes time, and that time manifests as an increase in latency on the serving job, and that's hard to fix. And this paper talks a fair amount about that. So, quick closing thoughts. As I mentioned, the ad hoc exploratory techniques that we get from those tools, the ones that exist to improve usability, accessibility of this technology, this is where we get innovation, right? This is where we get the next page rank, right? But we need infrastructural robustness and efficiency, represented by the things I talked about in terms of workflow and data management and quotas that I didn't even talk about, and efficiency in terms of utilization, to actually turn the clever stuff that we come up with those tools into something that we can actually get value out of, business value out of. Putting these two pieces together is really hard, and so the one takeaway here is we need to focus on the infrastructure. And I'm not smart enough to do the first stuff, the first part. I'm trying to get the infrastructure to be reliable, and it's a hard problem. That's it. Questions? Thank you. Anybody have a question?
Questions for Jeremy?
No questions. It's on Rick.
It's always hard to get the first question out.
Someone's got to have a question. Len.
So do you find much resistance to learning about infrastructure within Google?
Yes and no. So there's certain kinds of infrastructure that are there's unpopular to work on, right? There's certain pieces of this that's good enough, right? That doesn't need to be innovated on. We don't need another, I don't know, we don't need another, whatever I come up with, there's going to be some reason why you do need one. But we don't need another configuration language. This is my favorite one. Although I don't necessarily even agree with that. But let's imagine we don't. We don't need another, so the existing one that we have is fine. So getting people to actually work on it and maintain it with respect to sort of technical debt, and if you leave it alone, of course, it's going to rot because the rest of the ecosystem around it is changing. So it needs care and feeding. So there's that kind of infrastructure, getting people to care about that. Like I've got dedicated teams that just love that and do really a fantastic job at that. But that's generally not all that popular. Other places people love just working on being able to innovate on the infrastructure itself to make it sort of without changing the contract to the user, making the underpinnings more efficient and more reliable and faster and more awesome. So yes and no. Google's weird though. Like our engineers think differently.
Other questions?
Whew, getting off easy.
I'll ask one.
Okay. Then I'm not.
You're not done. So of the 128 or so tools that you mentioned in the course of this talk, how much time and effort do you spend worrying about dependencies between them, dependencies between versions of them, upgrading, and so forth? How big a task is that for you?
So it's a big task. Google internally has got a really weird, I keep saying that, a very atypical model. We don't version anything. I don't know if I'm allowed to talk about this. I'm probably not, right? We don't worry. If I find out later that I can talk about this, then I will. But we don't generally, for our internal systems, worry about inter-service versioning. We have other ways to solve the problem. But from experience working with the open source components I mentioned before, right? Hadoop is a big bag of weirdness. Then yeah, like when I was at Yahoo, to upgrade a Hadoop cluster, you basically have to tear it down, right? Like there's no in-place, at least there wasn't then, no in-place update possible because the wire protocol is, there's a binary dependency on the wire protocol. So if you want to update any component, you have to update them all. And then you've got to make sure that those versions all fit together. So yeah, it's really a hard problem. Now in our public-facing APIs, right, Google's cloud APIs that we expose to, lots of care goes into versioning those carefully because that's a public interface.
Maybe I have to buy you a drink to get the other story later.
Yeah.
Okay, let's thank Jeremy.
Thank you.